right, so a couple announcements before we get started. Um, I forget if I mentioned this on Tuesday, so I'll mention it again. In terms of the test being returned, I am expecting that the Fridays of last week will have their tests marked by late this week, ideally tomorrow. For those of you who had your test on Monday, then it should come forward sometime over the weekend. For those of you who do have a Monday tutorial, obviously Monday is Thanksgiving, so first of all, a early or premature have a good long weekend. But because of that, obviously you won't have your tutorial on Monday. So this week's tutorial will be made available. The tutorial and solutions will be made available tomorrow evening. So for you, those of you on Monday, the solutions will be provided over the weekend as well. That way, whenever you are taking a look at that, the solutions will be there, because unfortunately there's just not a tutorial. And also because of that, and in general, as always, feel free to fire me off an email if there's something in the tutorial that was confusing. If you have any questions, feel free to ask me via email or set up an office hour if you would like. All right, I believe that's all the questions that I have. If you do have any questions about any of that, feel free to let me know. If not, on Tuesday, we talked about a bunch of equivalent properties and properties of matrix multiplication and stuff that we've seen, and combining all the ideas we've seen so far. So that's going to allow us to prove something that we suspected for a very long time, namely what we have in front of us right here. Now, before I set you loose and to give this question here a try, what is this actually showing? So this statement here, show that if x1 and x2 are two different solutions to ax is equal to b, then some other random thing is a solution to ax equals b. What is this technically showing? It's something that we already know. So it's nothing that we didn't already know, but what is the implication of this particular rule that we're about to see why is true? Oh, don't look at the list of equivalent statements. This is not connected directly to the list of equivalent statements. Right. If there are two solutions, and that's a big if, right? That's not always true. But if there are two solutions, then what are we creating here? If there are two solutions, then what are we creating? How many solutions can we create? Right, infinitely many. So technically, this is the proof to what we've known, basically known to be true, maybe without proof, but known to be true since section 1.2. If we had two different solutions, we can get infinitely many solutions. So I'll give you a couple minutes to try and show this rule using some of the ideas we've seen so far, that if x1 and x2 are solutions, then this other thing is also a solution to the same equation. So I'll give you a couple minutes to give that a try. If anyone has any questions, feel free to fire them off in the chat. So what I'm saying is if x1 and x2 are two different solutions to this equation, then what we're saying here is we can create more. We can create more solutions, because this is a solution for every real number k. So we have infinitely many choices for this letter k right here. Which means if we let k equals 1, we get a solution. If we let k equals 2, we get a solution. 3, 4, 5, we get solutions. So what we're saying here is if x1 and x2 are two different solutions, then we can create infinitely many solutions by taking all the infinitely many values of k. So that's the big picture idea behind what we're doing. It's not how we'll show it, but it's the big picture idea of what this gives us. All right, so if you're partway through doing it, feel free to keep and finish it off. For those people who might be a bit stuck, because I mean it's theoretical, so it makes it a bit more complicated. Let's just make sure we're all on the same page. So what does it mean to be a solution to any equation? In this case, it's ax equals b, but in general, what does it mean to be a solution to any equation? Yeah, when you plug it in, the left-hand side and the right-hand side are equal. Right? If I gave you x plus y equals 7 and said, is x equals 3, y equals 4 a solution? Is the answer yes or no? Yes. You plug it in, you see if it satisfies the equation. So that's what we're trying to do here. We're trying to say, if we plugged in x1 plus rest of this nonsense into this equation, that it's the left-hand side and the right-hand side are equal. So that's how we can show whether it's plugging in numbers or whether it's plugging in an expression like we have. It's the same idea. You plug it in, you see if the left and the right-hand sides are the same. That's what it means to be a solution. So the general idea before we do it is if ax1 is equal to b and ax2 is equal to b, we want to show a times x1 plus k, if we plug in this, that it's also equal to b. So this is the idea of what we're trying to do. Given these two bits of information, show that this left-hand side is equal to the right-hand side. So that's what we're trying to do. The rest of it is a combination of matrix properties and stuff that we've seen a little bit of since section 1.4. All right. So that's what we're trying to accomplish. So how do we do that? How do we show this expression right here? Yeah. We want to show the left-hand side and the right-hand side are equal. Is it better to start with the complicated side and show it's equal to the nicer side, or start with the nice side and show it's equal to the complicated side? Start with the nicer side or start with the nicer or the complicated side? Yeah. Is it easy? Is it easier to simplify something or complicate something? Yeah, it's easier to simplify, so let's start with the complicated. Left-hand side, and we're going to use nothing but these two statements and multiplication of matrices properties. So what's the first property we can use? What's our first property? I still haven't seen it. Right. The distributive property that we can multiply over the addition. So that's ax1 plus a times kx1 minus x, or x2 minus x1. All right, beautiful. No, you don't need to know the name of the properties, but it helps when I'm asking them in the chat if you do. If I say it 50 more times, then everyone's going to know. All right, I'm going to leave the left term here alone. So what can we do with this second one? Distribute the k. Okay, distributing the k is not wrong, but it's also not necessary. So it wouldn't have been wrong to distribute the k. So the next property says factor out the k. Wait a second, that changes the order. Are we allowed to just change the order? Right, it's a constant. Yeah, k is a constant. Because it's a constant, we can factor it out. If k was a matrix, we couldn't. Although if k was a matrix, we'd have bigger problems of whether things were defined. But since k is a constant, yes, that can be factored out. And somebody said distribute the a again. Definitely can do that. And so that's ax2 minus ax1, using the distributive property again. All right, so what's ax1 equal to? What's ax1 equal to? B. Why is it equal to B? What was given? I don't remember seeing ax1 equals b in the question. Right, because x1 is a solution. That's right. Since x1 is a solution, ax1 is equal to b. What about ax2? Also equal to b. B minus b is 0. K times 0 is 0. B plus 0 is 0. So that's equal to b, which is our right-hand side. So if x2 and x1 are solutions, what we've done here is create infinitely many solutions. So that gives a formal proof to the idea of any system has either 0, 1, but if it has more than 1, it has infinitely many. All right. Any questions about these ideas before we try a couple other things? All right, so let's get back to our list of equivalent statements that we kind of saw right here. So just a reminder again on Tuesday. So what this means is that either all of these statements are true or none of these statements are true. And I had a wonderful email yesterday. I don't know if it was this class or my other class. I had a wonderful question based off of something I said in the videos that may or may not have confused them, which was being the opposite of kind of this thing right here, that it has exactly one solution for all b. I said in my video, something that is completely true. Yeah? Yeah, this is the one A04 OneNote page. What day of the week is this? Yeah. So I said in the opposite, um, that the opposite of this was that if A was not invertible, we got no solution or infinitely many solutions. So I do want to make sure I clarify something. That is a very true statement. That's technically not the opposite of what we have right here, that it has exactly one solution for all B. Technically, the opposite is that it might not have one solution, but not that it's impossible to have one solution. So I just wanted to clarify that. Um, if you were watching the videos, it does turn out to be the case based off of other reasons that AX equals B, if A is not invertible, has none or infinitely many. But technically, that's not the opposite of this statement. It would require more proof. All right, anyway, so we have this list of equivalent statements. Either they're all true or they're not true. So if A is not invertible, what does that tell us about the consistency? If A is not invertible, what does that tell us about the consistency of AX is equal to B? So does that mean that it is inconsistent for all B? Right. It means that it's inconsistent for some. It still might be consistent for some, but it's inconsistent for others, which might naturally lead to the following question. So find conditions on B so that this is consistent if A is this matrix right here. So it's certainly not obvious that A is not invertible. We'll certainly see that along the way, that A is not invertible. But if A is not invertible, we know it's consistent for some and inconsistent for others. So this question is about find the B's for which it is consistent. So I'll give you a couple minutes, give this a try, and then we'll talk about it together. Okay. So if you're still working on it, as always, feel free to keep working on it. For those of you done, or for those of you who got stuck. So we're finding conditions on the matrix B so that this thing here is consistent. So any ideas as to how we could find the B1s, B2s, and B3s? for which this is consistent, because if you believe me that this matrix is not invertible, then it's going to be consistent for some and not for others. And as somebody mentioned wonderfully, we can turn this thing into an augmented matrix and just row reduce and then figure it out. So 1, 1, 1, here's our coefficient matrix. We augment it with our constant matrix, and then we row reduce until we get into REF. Do we need to be in reduced row echelon form, or is REF good enough? REF is fine. So as we've mentioned quite a few times, finding the solution from reduced row echelon form is easy, but row echelon form on its own is good enough to figure out how many solutions there are. And since this question is about, is the number of solutions one or more, then we can get that directly from the row echelon form. All right, but now it's just a glorified row reduction question, and it's been almost a month of doing that, so should be fairly good at it. So subtracting 2 times row 1 from row 2, 3 times row 1 from row 3. As always, these are not the only elementary row operations that get the job done, but they work. And 0, 0, 0, B2 plus B3 minus 5B1. And we have our matrix in row echelon form, or at least the coefficient matrix. So when we say put the matrix in row echelon form, what we really mean is put the coefficient matrix into row echelon form. The constants are going to do what the constants are going to do, but the coefficient matrix is what needs to be in row echelon form. All right, so again, first things first, what about this can tell us that our matrix wasn't invertible? Technically, that's not the question, but I'm letting people get caught up on the copying. All right. Here's our row echelon form of the original matrix. We get a row of zeros, so it can't row reduce down to the identity. So right from there, that's one of our equivalent statements, that the row reduced echelon form of A is not the identity, which means the matrix isn't invertible, it's not consistent for all B, and all of these statements are false. Right. So that's what we suspected, but we got confirmation of that. So what are our conditions on our B's in order for this thing to be consistent? To be consistent. The left-hand side and right-hand side of what? That's right, of our last row. In other words, B2 plus B3 minus 5B1 is equal to 0, which is a perfectly fine final answer, although we can write that in a slightly nicer way. B1, B2, and then if we moved stuff to the other side, B3 would be 5B1 minus B2. But like I said, this is a perfectly fine way to leave your final answer. That's the conditions on B. But if we wanted it in its matrix form, we could do that as well. All right, so this was an example of a matrix where AX is equal to B, where AX is equal to B was not consistent for every single value, and but we still have a way of figuring out which B's work and which B's didn't. All right, where did I get B2 plus B3 minus 5B1? I got it right from here. So we would need the left and the right-hand side of that last equation, the left-hand side is 0, so the right-hand side would be 0. How did I get what matrix? The original augmented matrix? Oh, I just added row 2 to row 3. Is that not what I wrote? I hope that's what I wrote. Yeah, that's what I wrote. Unless I did it wrong. Row 3 plus row 2. Oh, I see. Sorry. Remember, B was B1, B2, B3. And so if you solve for B3 here, yeah, that's what the question asked us to do. So find conditions on this matrix such that AX equals B is consistent. Yeah, that was the question. Sure, or if you wanted to, you could have B1, 5B1 minus B3, B3. You could have done it that way. Why does it have to be equal to 0? Well, what does this line here say? This is section 1.2. This is stuff we've been seeing for a while. So that would say 0x1 plus 0x2 plus 0x3 equals to the nonsense on the other side. That's just equal to 0. So that's just the same kind of questions we've been seeing from 1.2 in terms of being able to determine, is there no solution, one solution, infinitely many solutions. So yeah, B1 and B2 can be anything, but then B3 has to be something that satisfies that equation. So for example, you could let B1 and B2 both be 1, and then B3 would have to be 4. Why can't B1 and B2 be 0? B1 and B2 could be 0. Then it would be 0, 0, 0. That's consistent. That's always consistent. It's homogeneous. Yeah, B1 and B2 could be anything. All right, if you have more questions, feel free to keep firing it off. That's where I have the most fun. If you don't, feel free to move on and give this question here a try. I'm not sure what you mean by solve for the B2. I'll go back to the question for those of you who are here. I'll write down the question here. Yeah, I'm trying to have a hard time. I mean, the idea is we just wanted to find the conditions on B1, B2, and B3. So we're perfectly fine if we finished based off of that. If you wanted to put it into matrix form, then you would solve for one of the B's. in terms of the other ones and stick it into the matrix. It honestly wouldn't matter if we solved for B1, B2, or B3. Um, they would be completely equivalent answers. They might not look the same, but they'd be completely equivalent answers, regardless of which B we were solving for. Yeah, like that one. We could have done B1 is equal to B2 plus B3 over 5 and stuck it into the matrix as well. Any of those three possibilities work just fine. Um, I'm not 100% sure that this was your question, but yeah, we don't need to worry about this because this would say x3 is equal to what we have right there, which is part of the solution. But, I mean, all we care about is whether or not there is a solution, not what the solution would be. The only reason we're caring about this is because if this was not zero, we would get 0 equals non-zero. And as we've seen since section 1.2, if we get 0 equals non-zero, we get that it's inconsistent. And so that expression has to be 0 or else our matrix or our system is inconsistent. As for the other rows, they had leading 1, so we didn't need to concern ourselves with that. Yeah, B1 and B2 could be anything, and then B3 has to be whatever it needs to be in order for this last expression to be 0. Although technically, we could let, and this is over complicating it a bit, I think, but we could say B3 equals 1, B1 is equal to 5, and then solve for B2, right? So in general, we could let any two of them be equal to something, but then the third one is forced. It doesn't really matter which two you give, but as soon as you give two of them, then the third variable has to equal whatever it needs to make the whole thing 0. I did. Somebody wanted to see the note, so here's the note. So what I'm saying here for this one is you can't say AB inverse is equal to B inverse A inverse because we're trying to show that A and B are invertible. So even writing B inverse and A inverse is saying, well, A and B are invertible, and that's what we're trying to show. So that's what I'm saying in my note. We're trying to show AB is if AB is invertible, then both A and B have to be invertible, but you can't use that they're invertible to write this expression. Otherwise, it's the chicken and the egg. Can't use the chicken to get the egg, and can't use the egg to get the chicken. If you haven't heard that expression, ignore it, because it probably confused you. So my hint here was there might be one of our list of equivalent statements that might be easier to use than the definition of being invertible. So that was the hint for this. Fair enough. We're assuming here, and I think I put this in the actual question itself. No, I didn't. Oh, that should have been there. My apologies. So in this question here, it should also say that A and B are square in our matrix here. So it should say, suppose A, B are invertible and A and B were square matrices. Otherwise, this is not a true fact. So if A and B are both square matrices, where A and B are invertible. Thank you. All right. So, feel free to try and see if you can do this straight from the definition of being invertible. Unfortunately, I don't think it'll go very far. So we're going to use one of these equivalent statements to try, to try and show this. So are there any of these equivalent statements that you might think, given the fact that we don't know what A and B actually are, we don't have the matrix entries themselves, is there one of these that looks like it might be less awful to work with? Three? Okay. I'm not saying it won't work. So if we know, don't write anything down yet. So if we know, so don't write this down. If AB reduces to the identity, does A and B reduce to the identity? How can we show that? Technically it's going to be true, but how can we show that? Can anyone see a way for all the people saying 3? How can we show this? Yeah, I'm not sure either. Yeah, unfortunately, showing something can be reduced to the identity is usually involved with taking the entries and starting to row reduce. So without actually knowing them, I'm not so sure that that's going to be the easiest property to work with. Any other ideas as to a property that'll be easier to work with than the other ones? And I'm not saying it's easy. I'm saying less awful. Any other ideas? Product of elementary matrices? Okay. Okay. So if AB is equal to a product of elementary matrices, then can we write A equals something and B equals something? Keeping in mind, we don't get to choose what A and B are. We would have to solve for A and B. Yeah, I'm not sure about that one either. I'm not saying, so this one can actually be workable, but unfortunately it's not as obvious as, ooh, take these ones as being A and these ones as being B, because we don't get to choose A and B. All right, somebody suggested 2. Yeah. Using one that doesn't require us to know the entry. So if ABX equals 0, implies X equals 0, let's show that bx equals 0 implies x is equal to 0. So this is the one that we can show because it's involving equations and it's involving just matrix properties as opposed to actually needing to know what the individual entries are. All right. So we're going to assume that AB is invertible. In other words, AB, the homogeneous system, only has the trivial solution. And we're going to show the exact same thing is true for B. So we're going to show that bx equals 0 only has the trivial solution. So that's going to be our plan. So this is what we're trying to show. So how do we show a statement like that? How do we show that bx is equal to 0 has only the trivial solution? We'll get to ax. You're right. We do need to worry about a as well. I'm going to start with b, and then we'll come back to a. But I claim bx is a little bit nicer to work with than ax. Can anyone see why bx might be a good place to start instead of ax? Why is bx? Yeah, because right here, the b is right next to the x, and we can rearrange the brackets. But what can't we do? We can't change the order, so I can't take this and stick the a next to the x. The b is next to the x, so we're going to start with that. But yes, we'll have to address a in a little bit. All right, so we want to show that this is true. So this is an implies. So this thing here implies that x is equal to 0. So logically speaking, how do we show something like that? Now that's the other way around. You're letting x equals 0 and showing bx is equal to 0. That's the opposite. So here's the idea. We're going to let bx equals 0, and then we're going to show x is equal to 0. And we're just getting the ideas down. Obviously, there's some steps in the middle, but that's what we're trying to do. But let's be careful that we're doing this in the correct order. The classic mistake is people saying, well, let x equals 0 and then start to calculate bx. And that's the opposite of what we have. All right. Somebody mentioned, wonderfully, can we multiply both sides by b inverse? Can we multiply both sides by b? And that would seem to be the easiest way. Can we multiply both sides by b inverse? So we're going to show b is invertible by multiplying by the inverse. That would be like saying, I'll show 0 is equal to 1 by just saying that 0 is equal to 1. No, we can't do that. Unfortunately, we can't multiply by b inverse because we don't know if b is invertible, right? Until we know b is invertible, we can't multiply by the inverse. So unfortunately, that's not going to work. So suppose bx is equal to 0, and our goal is to perform some steps and show x is equal to 0. Now, what is the one thing that we know? We don't know if b is invertible, but what do we know? We know B is square. I mean, we know AB is invertible. That's what we know. That's the only thing that we know. A times B is invertible. We don't know if B is invertible, but we do know A times B is invertible. So what should I do if we know stuff about AB? What should I do to this equation? Yeah, we're going to multiply by, I've seen a few options fired off in the chat, and that's wonderful. What should we multiply by if we want to get AB there? Yeah, we're going to multiply by A. Of course, multiplying the zero matrix by A doesn't change anything. So now we have that ABX is equal to 0, and it's associative, so that's great. So what's the benefit of having AB here instead of just having B? Yes, this would be similar to that statement, for sure. Yeah, now we couldn't multiply by B inverse before. We couldn't multiply by B inverse because we didn't know B was invertible. Now it's A times B. We know that's invertible, so as somebody mentioned above, what can we now multiply by? We can multiply by AB inverse. Of course, you have to multiply the other side by AB inverse, but that's fine. And then the inverse and that thing cancel off, and we get that x equals 0 is the only solution. So there we go. So we've shown that bx is equal to 0 only has the solution x equals 0. And the only thing we used was that, other than matrix properties, is that AB inverse existed. We didn't use that B inverse existed because we never multiplied by B inverse. We used that AB had an inverse in that very last step. All right. So we showed that bx equals 0 had only the trivial solution. So since bx equals 0 has only the trivial solution, what does that mean? Based on our list, of equivalent statements, since bx equals 0 has only the trivial solution, well, this is an equivalent statement list. If one of them is true, all of them are true, and therefore B is invertible. Wonderful, but what about A? So we'll have to get to A. But yes, we've managed to show B is invertible. Technically, that didn't show A was invertible, but fortunately, knowing one of them helps us find the other. All right, so any questions about showing B was invertible before we turn our attention to A? By the way, we're going to use this. I mean, it's an example on its own, but we're going to see this being an important property when we move on to chapter 2. There's something in chapter 2 that's going to need this fact, which is, the main reason why I'm focusing so much on it is because we're going to use it. All right, so what about A? So if we know B is invertible, then how can we write A in terms of these other two matrices? We know something about AB, we know something about B. So how can we write A? being careful about the order. We can take AB and multiply by B inverse. Why can we do this now when we couldn't do it before? Like, why didn't we do B equals to A inverse times AB? Why didn't we do this before? Right, because we know that B is invertible now. We couldn't do this until we knew that B inverse existed. Beautiful. I hadn't quite finished my line yet when I wrote A equals A times B. All right, so super duper, A is equal to this. Why does that matter? Why does this matter? I mean, sure, it's true, but why? How does this help us show that A is invertible? I'm not sure how A equals AI. I mean, that's definitely true. A is equal to AI. I'm not sure how that shows A is invertible. All right, well, what do we know about AB? What do we know about AB? It's invertible. What do we know about B inverse? Is B inverse invertible as well? Bingo, it is. So now we have two matrices multiplied together, and that is something we knew from earlier. This is a product of two invertible matrices. And if you remember back in 1.4, 1.4, we saw that a product of two invertible matrices was also invertible. So this was an indirect way of showing that A was invertible. We first showed B was invertible, and then just multiplied two invertible matrices together. But that was something we knew. Multiplying invertible matrices together keeps you invertible. What we're doing in this question is the opposite. If the product is invertible, then the individual matrices have to be invertible as long as they're square. All right. So, any questions about either this example or some of this list of equivalent statement stuff, and which is where all this kind of came from? Before we leave theory class and go to example class. Not completely sure I understand that question. The A equals A, which is consistent. I mean, that's a true statement. I don't see how it applies here. All right, so now we're getting into philosophical in the chat. Does math start with examples and get theoretical, or does math start theoretical and move on to examples? It's technically the second one, unless you teach and don't want to blow students' minds, and so you treat it like it's the opposite. But in reality, it starts with the theory, because every single section starts with, this is the definition of something. Well, that's why we do both. All right, so section 1.7 is talking about a few special matrices. So symmetric, diagonal, upper triangular, lower triangular. So we're going to look at all of them in this particular example. Let's just remind ourselves what all these things mean. What does it mean to be symmetric? Either something vague or something specific. What does it mean to be symmetric? A is equal to its transpose. Exactly. A is equal to its transpose. That's what it means to be symmetric. Beautiful. The main diagonal acts like a mirror. I like that too. What does it mean to be diagonal? Yeah, all the entries off. All the entries off the main diagonal, which actually sounds kind of weird. The definition of being diagonal doesn't actually care about what's on the diagonal. It cares about what's off the diagonal. Beautiful. What does it mean to be upper triangular? No. What does it mean to be upper? Everything below the main diagonal is 0. Everything below the main diagonal is 0. Again, the definition of being upper triangular actually cares about what happens in the lower triangle. And vice versa for lower triangular. All right, so let's take a look at one. Let's do all of these for symmetric. So, make ourselves a little bit of a table. So symmetric, diagonal, upper T, lower T. All right, so first one. Is it symmetric? I paused it. Let me unpause it. First one, is it symmetric? No, why not? Why not? Right, A transpose is not equal to A. If we take the first row of A, does it match the first column of A? That's what it would be, and the second and third as well if it were to be symmetric. But the first row does not match the first column, so the transpose is not equal to the matrix itself, and as such, it is not symmetric. All right, so any questions on what it means to be symmetric, either for the first example or just in general, before we whip off the next three? All right, second matrix, symmetric or not symmetric? Indeed it is. If we're checking that, first row matches the first column. First row and first column are the same. Second row, second column. Both of them are 0, 2, 0. Third row, third column. Both of them are 0, 0, 3. So the rows match the columns, aka the matrix matches the transpose. All diagonal matrices are symmetric then. That might be a rule. What about number 3? We'll come back to that. What about number 3? No, yeah. This one's no. Very similar reason for number 1. Take a look at the first row. Take a look at the first column. We can see that they are in fact not the same. So the transpose is not equal to the original matrix. What about number 4? Everything is a 0. That looks pretty symmetric. No? No. No. Why does it have to be square? Why does it have to be square? Yeah. If we take 0, 0, 0, zeros and transpose it, isn't that just the 0 matrix? Isn't the transpose of the 0 matrix just the 0 matrix? Right, because not only do the entries matter, the size matters. And so if we took the transpose, while it might still be a zero matrix, it's not the same. So a lot of people have been saying in order to be symmetric, the matrix has to be square. Technically, that's not part of the definition, but it is certainly a consequence. If A transpose equals A, it has to be a square matrix or else the sizes aren't even the same, let alone the matrix itself. And in fact, all these things would fail for the same reason. If the matrix isn't square, then you can't be any of these things. All right, any questions about symmetric? Transpose equals to A. Cool, diagonal. How is this not theory? I talked about what it means to be symmetric. That's theory. Anyway, sorry, I'm getting philosophical. Diagonal. Is the first one diagonal? It's okay, I'll take away the number soon enough. No, it's not diagonal. Why not? Yeah, so to be diagonal, everything off the main diagonal has to be 0. And these off diagonal entries are certainly not all 0. So that's not diagonal. How about numero 2? Yep. If we take a look at all the entries off the diagonal, they're all 0. How about number 3? Number 3, yay or nay? Nay, that's right. Now, I picked some poor examples, and I realized this in my class yesterday. I picked some poor examples because if you're not careful, this might seem like being symmetric and being diagonal are the same thing. That's not true, right? I mean, there are certainly some examples. Well, tell me. So if you are symmetric, do you have to be diagonal? So if you're symmetric, do you have to be diagonal? No. So here's an example of a symmetric matrix that isn't diagonal. However, if you're diagonal, do you have to be symmetric? Yes. So all diagonal matrices are symmetric, but not the other way around, despite what my columns might look like. Somebody was relating it to triangular. We're going to get to that next. So for 1, is it upper triangular? Actually, let's wrap them up together. Is it upper, lower, both, or neither? Neither. We got entries, non-zero entries above and below. Non-zero entries above and below, so it is neither upper nor lower. What about number 2? Number 2, upper, lower, both? Both? Beautiful. How about number 3? Is it upper, lower, both, or neither? It is upper triangular. So this is the one that is going to confuse some stuff. So upper triangular means everything. Upper triangular means that all the non-zero entries are above the triangular. So just like with diagonal, being upper triangular, what it means actually is talking about the stuff below. So being upper triangular means everything below the main diagonal is 0. Just like for diagonal, everything off the diagonal is what we looked at. So being upper triangular means that everything below the main diagonal is 0, which is true for number 3. Being lower triangular would mean that everything above the main diagonal has to be 0. And that's not true. So that is our upper and our lower triangular matrices. All right. So any questions about what it means to be symmetric, diagonal, upper, or lower triangular, although upper and lower we're not going to see much of right now, but that'll become useful in chapter 2. All right, so just to get used to some of the properties, assuming A and B are symmetric, I claim that 3 of these things are symmetric. So if A and B are symmetric, I claim that 3 of these are symmetric. Which ones are they? Which 3 of these are symmetric and which one might not be? And quite frankly, none of this is stuff we didn't do in section 1.4. We just didn't use these words. So which 3 of these are true? Which one of them is not necessarily true? 2 of them should be fairly obvious. 1 might require some more thought. Okay, I'm asking 2 questions at once, and that's stupid. So feel free to fire off in the chat which 3 that you think are true. Which 3 do you think are true? Two, three, and everyone loving 2, 3, and 4. Is that just peer pressure, or is everyone confident? All right. Confident. I like it. Be confident and wrong, and that's great. That's right, they're all correct. And I'm just messing with you. All right. All right, so just in terms of idea, let's stick with the idea to show, if we want to show C is symmetric, how could we show C is symmetric again? Just in terms of how do we show something symmetric? All right, show C transpose is equal to C, starting with the more complicated side. Beautiful. So let's take a look at number 3, Ka. So what is Ka transpose? So again, if A transpose is equal to A and B transpose is equal to B, is there any rule we have for Ka transpose? Any property that we know is true? Is that just equal to K times A transpose? Indeed it is. So that's equal to Ka. Bingo. Wonderful. 4. A transpose transpose. That's going to be equal to A. Is that equal to A? And that's just A transpose. All right. Bang. Beautiful. Let's go to 2. AB transpose. Do we have a rule about how to do AB transpose? Assuming they're both, well, no, this is actually true regardless of whether they're square. What's AB transpose equal to? Dun, dun, dun. Is that equal to A times B? Nope. At least not always. Sometimes, but not always. It is not always true that if A and B are both symmetric, so here's two matrices that are symmetric, multiply them together, and you get a non-symmetric matrix. As for one, yes, A inverse transpose and A transpose inverse would be the same. So yes, it was 1, 3, and 4. So the correct ones were 1, 3, and 4. The inverse of a symmetric matrix is symmetric. A constant multiple of a symmetric matrix is symmetric. The transpose of a symmetric matrix is symmetric. That shouldn't be very surprising. But if you take two symmetrics and multiply them, it is not necessarily symmetric. In fact, the only way the product of symmetric matrices can be symmetric is if they're also commutative, which, as we know, doesn't always happen. Alrighty. So, any questions about these before I promise you some more numbers and we can actually look at numbers again? Alrighty, so we probably won't get through all of these. I'm just going to talk about them a little bit. This is where we're going to start off with on Tuesday. So feel free to actually start multiplying them together, but we only have a couple minutes. I just want to make sure everyone's on the same page as to what these things mean before actually going forth and actually computing them. So what do we do? What is A squared? A times A, wonderful. So is A squared equal to 1, 9, 4, 16? No. Well, probably not. No. Right. A squared is A with A next to it. And you actually have to multiply them out. All right, A cubed. What about A cubed? How can we find that? A times A times A. So whatever answer you get from A squared, multiply them together with another A, and away you go. Beautiful. I hope you know what this means. What's A to the negative 2? Is it the inverse of A squared, or is it the square of A inverse? Is it the inverse of A squared, or is it the square of A inverse? Yes, is the appropriate answer to that question. I honestly forget how it's defined because they're both the exact same thing. Okay. So you could do it either way. The inverse of A to the negative 2 can be thought of as either the inverse of A squared or the square of A inverse. Similar with transpose, it doesn't matter which order you do it. All right, we're out of time, so we'll start off with this on Tuesday. If you have any questions, let me know. If not, have yourselves a fine Thanksgiving long weekend, and I'll see you next week. Just a reminder, there is no tutorial on Monday. So take a look on the Learn page tomorrow late afternoon or something, maybe in the evening, where both the tutorial and the solutions will be posted for Monday students who don't get one.